Got ourselves a ladder problem here. A beam AB has mass m, length 2a. Bring the mass in a minute. It rests in equilibrium with A on rough horizontal ground, so there's going to be friction, and B against a smooth vertical wall. And it's inclined on the horizontal at an angle theta. As shown, coefficient of friction is mu. Modeled as a uniform rod. Right, so now I can bring in the weight acting in the very middle. It's going to be mg, and this here is going to be A. And I can also put on a normal to the beam, and then this angle will be theta. And it's resting in a vertical plane perpendicular to the wall. Okay, we're asked to show that mu is greater or equal to a half cot theta. So let's add on any other forces that we have. There's going to be a normal reaction coming from the ground. I'm going to label this capital RA. There's going to be a normal reaction coming from the wall. Must be pushing it normal to the wall, so it's going to the left, and that's I'm going to call RB. And then let's bring in the friction. So at this point, we can see the friction has to be going to the right. I mean, it makes intuitive sense, like the ladder would be slipping to the left otherwise, but also you can see it needs to counter the normal reaction from RB. There's no way it could be in equilibrium otherwise. So I'm going to call this FA. And those are all our forces. So the next thing to do is to take moments. I'm going to take moments about A. You always want to do this because it just straight away eliminates RA and FA from the problem. So if I take a look at the clockwise movement, that's going to be coming from mg. Well, it's going to be the component of mg acting perpendicular to the beam, which is mg cos theta. Remember, I can turn this into a little right angle triangle here, and then this here is the adjacent. I could write down the adjacent divided by the hypotenuse, mg, is equal to cos theta, and then rearrange it. And it would be that one that would be sine theta if we need it. Now remember, for moments, it's that force, that perpendicular force, times the distance. So don't forget about that. We're going to be timesing by A. And then this is going to equal, again, the component of RB that's acting perpendicular. Now, I mean, you can draw a line like this, but I think it's just easiest personally to put this angle as theta. Okay, because we've got ourselves a Z. And then my little triangle would actually look like this. So I'm going to be doing sine theta here because it's opposite. So it will be RB sine theta times 2a. I can cancel out the a's. And then rearrange to find RB. So it's going to be mg cos theta divided by 2 sine theta. I'll just rewrite that as a half. Mg divided by 2 is the same as times by a half. And then cos theta divided by sine theta becomes cot theta. Now for resolving forces. Let's look horizontally. You typically just take moments once and then everything else is going to work out from here. It must be that Fa, that frictional force acting to the right, is equal to Rb, the normal reaction acting to the left, because those are the only two forces acting horizontally. So Fa is also going to equal a half mg cot theta. And if I look vertically, then it must be that Ra, the force from the normal reaction going up, is equal to mg, the weight going down. Now let's bring in the frictional modeling force. So Fr in general, but here it's going to be Fa is going to be less than or equal to mu Ra. We are having to deal with a less than equal to because we know it's in equilibrium. The friction will only take the amount that it needs to stop the ladder slipping. And then we sub in. So it's going to be a half mg cot theta is less than or equal to mu mg. And I can divide through by mg. So mu must be greater or equal to a half cot theta. That's what we're asked for. Now for the second part. A horizontal force of magnitude kmg is now applied to the beam at A and acts in a direction that's perpendicular to the wall and towards the wall. So let's modify our diagram. Hmm. So we've got the normal reactions exactly the same, but now there's going to be this new force acting this way, kmg. And we don't actually know at the moment which way friction is going to be going because if kmg is not very big, friction could still go to the left, whereas as kmg becomes sufficiently big, suddenly the ladder will be trying to slip to the right rather than to the left. So just for the moment, I'm going to remove the friction. I know I need to bring it in a minute. And we're also given that tan theta is 5/4, and now mu is equal to a half. So we could do lots of the similar things again. We know, well, we don't know that RB is now equal to FA, for example, but there are some things we do know. For example, we still can take moments about A and get that same result that RB is a half mg cot theta as before. But I can work out what it is because if tan theta is 5/4, then cot theta is 4/5. And 4/5 times a half becomes 2/5. So it's going to be 2/5 mg. If I look vertically, I'm going to get that Ra is equal to mg as before. Okay, but I can't just say that the friction is equal to 2/5 mg, but what I can do is bring in the friction because it's in limiting equilibrium. It's going to equal mu times Ra this time, and hence it's going to be a half because mu is a half mg. And then because this is, we can see this is 2/5 mg pushing to the left. Um, and then the friction is going to be larger than that. So there's no way that the friction could be acting to the right because the frictional force itself would be bigger than 2/5 mg. So I know I'm going to do this in red. It's still just forces on the ladder, but I know the friction's actually going this way. It's only at that point that we actually know that for sure. But I can write, I'll write it as FA on here, but now I know it's a half mg. And everything's going to come together now. So let's look at forces horizontally. It must be that RB plus FA is equal to kmg. Forces to the left equal the force to the right. So that's 2/5 mg plus a half mg is equal to kmg. And that's 0.4 plus 0.5. So k is going to equal 0.9. You have to get it the right way. You can't just put it right to the right and hope it will work out with negatives. It won't. You'll get the wrong answer for k. So be really careful, I would say, making sure you understand that it actually switches and starts acting to the left. Well done.